Hey guys, it's Dakota Wixom here from QuantBros.com, and today I'm going to show you how to generate random portfolios on a large scale and how to calculate efficient frontiers, accelerating the entire process using distributed computing. In order to accelerate the project in R, we're going to be using a solution from Techila Technologies. They've got a package for MATLAB and R and Python that will link directly to your AWS, Google, or Azure instances, and even to your in-house solutions. Utilizing Techila for this project is going to make a really big difference for us. Distributed computing in general is just going to allow us to break up our initially massive task, which they call a project, into hundreds or thousands of little pieces, smaller computations called jobs. These jobs can then be channeled through Techila, for example, into our own cloud environment or into our own in-house environment if we've got one. The jobs are then distributed across hundreds or thousands of CPUs, allowing for the CPU time it would normally take on one machine to actually be distributed across multiple machines. These results are then sent back to us through Techila. This means that at the end of the day, the calculation can be performed orders of magnitudes faster than on just a single machine. So we're going to be building hundreds, thousands even, feasible portfolios using S&P 500 sector ETFs, testing the effect of changing the max allocation constraint in a single asset, which is just a simple random portfolio generation constraint, which actually has a huge impact on your portfolio outcomes. You can then walk through this tutorial using a small number of simulations and assets if you want to prototype the code on your local machine. And then when you're ready for thousands of simulations at rocket speed, you can then flip on the switch, turn on your cloud solutions, turn on Techila, and we'll be ready to go. We'll even step you through the process of accelerating your downloading of sample data using Techila and some handy-dandy plyr functions, which you're probably going to be familiar with if you've used R at all. Alright, so without further ado, let's get right into it. So you might have to set some environment variables here. I like to set my working directory here on line 5. I also am pointing to my Java home and to the Techila SDK root. You may or may not have to do this. It depends on your installation, but hopefully you're already past that point. I'm also going to load in some libraries that we're going to be using. Now, if you don't have these libraries, just type install.packages, and then, of course, write the name of the package. So if it's our portfolios, then we're going to do that. And that should install it for you. Now, if you have all of these packages loaded, then you're ready to go. Just run the library. So we're going to use our portfolios. That's for the random portfolio generation. And we're going to be using plyr. That's for merging and applying functions. It's very useful for working with data in R. QuantMod for downloading returns. We're going to use performance analytics for charting and calculating return metrics. And we're going to be using ggplot for visualizing data. And reshape2 will be for melting objects to be passed into ggplot. So ggplot takes a very specific format of data in order to run. So reshape2 is great for dealing with that. Of course, we're going to need Techila, and when you're installing Techila, you're going to have to make sure you have access to the rutils package and the rjava package. Now, I'm going to assume you've already done this for the sake of this tutorial. If you need more information on installing Techila, you can go to their website. And if you just want to follow along without Techila, if you want to follow along without a cloud-based solution, then you're welcome to do that. You're just going to have to run a smaller number of simulations for the sake of this tutorial. So now I'm going to run register do Techila. Of course, if you don't have Techila installed, then you're not going to be able to do that. I'm also going to make a variable called isParallel. And for the sake of this tutorial, we're going to write true. Now, if you are not going to be using Techila, just make this false. And then if you decide to in the future, or if you have some other cloud solution that you'd like to use in combination with this tutorial, then you can just change the variable from false to true. And we're going to set everything up to run dynamically that way, so you can decide whether you're going to run it locally or cloud-based with just changing one variable. Now, in order to make sure that our Techila installation is running, let's just write a really quick program, right? So let's write a for each loop. So we're going to do for each, and then we're going to say b equals the vector from 1 to 4. We're going to do dot combine, right? Combine the results together using the cbind function. And then now this is a really unique syntax for this. We're going to do %, colon, %, and then for each a 1 to 3, whoops, a equals 1 to 3. Now we're going to do parallel, do par. This is saying, you know, we're going to run this parallel in the cloud, and we're going to do a times b. And this is just a really simple example just to make sure everything works. Now, if you are not using a cloud-based solution, you don't really need to run this, but we're going to go ahead and run this. Now, Techila is going to pop up, so I'm going to go ahead and enter in my password and then press OK. All right, now that we have that out of the way, it's going to go ahead and run the project here. You can see it doing all of that in the background. You can see it setting up the job. Now, of course, this is a extremely small number of simulations. This is, I think, 12 simulations for this example, but you know, we're just making sure everything works. So this is going to take a little bit of time to run while it connects to the cloud and all of that. Now, there's going to be a little bit of downtime. It's going to have to send data to the servers, right? And then it's going to have to run the calculations, compile it, and send it back to you. So depending on the size of your simulation size, it may not make sense, you know, to run this at all in the cloud. So you can see, for example, for this example, our acceleration factor is 0.16. That means it was actually slower than if we ran it on our local machine. And that makes total sense. We're running 12 simulations, right? Now we're going to be running thousands of simulations soon, so you're going to see that acceleration factor is going to go screaming past 1, clear into, you know, like 50s, 70s, you know, 100 times. So we're going to go ahead and move on here and just assume that that you've got your Techila installation all set up and you're ready to go. And if you're not, you're just going to follow along on a local machine. So first thing we're going to do is download data. So we're going to set up an object called tickers. And here, let me just enter in a few S&P 500 sector ETFs. So XLU, that's utilities. XLV, that's healthcare. We're going to do XLI, that's industrials, right? All the sectors. XLY, I mean, we could do real estate if we wanted to, but that's relatively new. Let's do XLK. And if you want, you can connect to your own database, load in your own data, right? But if you're following along for the sake of the tutorial, I figure, you know, it's going to make a lot more sense to just download the data so everybody has, you know, the same starting point, right? So now we've just got a vector of tickers here, and you can see that it's pretty straightforward. We're going to type in num assets just to keep track of how many assets we have. You can add more if you want. I mean, go for it. Length tickers, right? So now we have how many assets? Well, we have 8 assets. Easy. Okay, so now when we're downloading data, it's going to make more sense to say, you know, when's our start date, when's our end date. So we're going to go ahead and write that in here. So assign dates for downloading data. Okay, so we're just going to call this sDate equals as.date 2000. Let's go back. Let's go back to January 1st, 2000. And then for the E date, you know, the end date, we're just gonna make it today, right? If you want to use a different time frame, go ahead. But I'm just gonna run those lines here. So now we've got our starting and end date, and we're good to go. Next, we're going to actually have to pass in these parameters into a function. So I like writing little functions to download this data. I'm going to show you just an example of running this in combination with Techila. And, you know, if you're downloading a lot of data, this might be useful. But for this example, it's probably going to run slower than if we did it on our local machine. But that's fine. It's just an example to get you thinking about, you know, how to use this use this function. So, because you have to think a little bit differently. So we're going to just call this ticker data, and then we're going to use the lapply. That's from the plyr library. So again, make sure you have that installed. And then we're going to pass in tickers, our object, of course. And then we're going to make our own function here, which we're going to be applying to our tickers object. So it's going to take ticker, it's going to take sdate, which we have defined, edate, right, which we also have defined, and then now let's make that function here. So we're going to run get symbols. This is from QuantMod. In fact, give me a second. I'm going to actually zoom in for you just so it might be a little bit easier for you to see. So let's just go to appearance, font size. Let's go with 16, and yeah. Oh, maybe a little bit too big. Let's go with 14. All right, all right. Hopefully you guys can see this a little bit better here, and I'm just going to minimize this because we don't really need that yet. Yeah, all right. So we're going to type get symbols, and then we're going to pass in our ticker, right? And this is lowercase ticker because it's coming from our function. I'm going to say download it from Yahoo. From the start date. Oops. Start date, and then to our end date. Okay? And then auto.assign equals false. This means it's just going to return the data as an object instead of storing it to an environment. Now, this is really important because, you know, in the cloud, they're not going to share these nodes are not going to share the same environment, right? Unless we're passing in an environment object and telling it to store it to that. But then it might not be able to do. You might not be able to do that in parallel. So let's tell it to do it in parallel. Also, .parallel is the parameter that we use for all plyr functions, and we're going to pass in is parallel. Now remember, that's our Boolean object, so that's just true. So the same thing you could do is just write true here, or false if you don't want it at all. You could also just not include it. And then let's just tell it, you know, hey, sdate is sdate. You don't really have to write that, but it makes it a lot more clear. Edate equals edate, right? So now it knows that the value inside here is what we're passing it. And then we're just going to pass in a few parameters here. So this is real important. So make sure that whatever you're doing in the cloud, that the instances that you're spinning up have the same packages, right? So if you're running something with plyr and QuantMod, which, I mean, we are, right? You're going to need instances with those packages installed. Otherwise, it's not really going to know what to do. So we're just going to tell it that. We're going to say plyr and QuantMod. Okay? And now we're ready to go. So let's go ahead and download that data. So this is going to do this in parallel. It's going to send it to multiple instances. It's going to retrieve the data, right? And then it's going to send it back to us. We're going to combine the data into this object called ticker data. So from there, we're going to have to merge all of these prices and returns. We're going to have to calculate returns, right? And then we can move on to the next part of our project. And then we'll move on. All right, so there we go. That was pretty fast, and you can see it was actually, you can see it was into the cloud. Now, if we were downloading hundreds of stocks, it's probably going to be speeding that up for us, which is nice. But for this, we're just starting with a small example, okay? So now let's merge and calculate the returns, okay? So let's just call this object stock merge, all right? And then we're just going to do call, so we're going to merge on our object, which will actually be another lapply of ticker data, and we just want to extract, right, our adjusted close prices. So if you look at ticker data, we've got a list of objects, and then we've got multiple fields for each object. So I'm just saying, go through the list, find each list object, and then only take the adjusted close column, right? So we're going to go ahead and run that, and now you can see if you run head of stock merge, there you go. So we've got all the adjusted close prices for each of our sectors. And then we're going to calculate returns. So we're just going to call this stock returns. All right, equals, and then we're just going to use a handy-dandy function called ROC. It's just rate of change. And then we're just going to do na.omit of our stock merge. So I'm just saying, you know, hey, if you find any days where we don't have data for all these stocks, just ignore it. Now, all of these stocks are ETFs. They're highly liquid, so we're not really going to have any problems with that. But just for the sake of the tutorial, I'm going to throw that in there. And then what type of return? You know, do you want log returns? Do you want simple returns? And, you know, we're going to use simple returns for this example. It makes a lot more sense. And then just get rid of the first day because, I mean, there's not going to be a return for the first day. It's going to say NA, right? All right, so then we're going to run that line. And then if we check out stock returns, head, and there we go. There's your daily returns, okay? And now let's just rename everything. So call names of stock returns. All right, and then we're just going to pass in tickers. So we can get rid of that annoying dot adjusted at the end, right? So now if we head of stock returns again, there you go. Much easier to read. And of course we know it's returns because our object is called stock returns. So no problem there. Now before we move on, I'm just going to throw in a quick little chart here. So let's do a handy dandy performance analytics chart. Let's of our stock returns. We could call it our cumulative returns, all right, and these are geometric returns, so we're just going to tell it that, and then go ahead and run that. Now our plot is small here, so let me bring that up here and just give it a second to render. All right, there we go. There's our cumulative returns over time. You can see the drawdown and the daily returns, so we're going to create a portfolio out of these assets, right? All right, so let's move on to the efficient frontier generation. Okay, let's get to the good stuff. So let's go efficient frontier. All right, just so we're clear. How many simulations do you want to run? I mean, if you're running this locally, don't tell it to do 1,000 simulations. Tell it to do like 10 or 100 if you feel like sitting around, you know. But luckily we've got cloud solutions, so we can run a high number of simulations. We can run 1,000, 100,000, whatever we want. Now we're going to do this multiple times with different examples, but this is just a one variable simulation. So what I mean by that is we are just going to be running right now a constrained random portfolio generation function. It's going to say, all right, how many assets do you have? What random seed are we passing in? What's the probability that we're going to go long in the asset? What's the max weight? What objects are you looking at, right? So I'm just going to write a function that does this. And it's going to be pretty straightforward, so we're just going to call it function RandomSim. It's going to take the seed. It's going to take the number of assets, right? How many assets are we looking at? Now, prob long, if this is 1, then it's going to just give us all weights that are above 0. If that is 0, then it's going to give us all weights that are negative. And then max weight, obviously, you know, that means, you know, what's the maximum weight. If it's 25%, then we're not going to have a portfolio with a stock that has more than a 25% weight. So now let's create the closure here. So we're just going to get, we're going to run, this is from the R portfolios package, so make sure you have that installed, as I mentioned in the beginning. And then we're going to do random.general.test. All right, n equals num assets. Okay, and then p equals prob long, x.u equals max weight. All right, and then we're going to extract the solution. That's what the $x is at the end. And then we're going to calculate, of course, our portfolio return. So portret equals as.xts, right? We want an XTS object. We're just going to apply across the function, or across the object. We're going to do a sweep as well. And we're going to take our stock returns object. We're going to sweep across the columns. We're going to apply our weights, right? So essentially all we're going to do is multiply our weights by column, right? So that just gets your portfolio. returns, or weighted portfolio returns. And then now we just want to sum across the columns, which will give us our actual portfolio return. And that function is good to go. We just have to remember to return something. So let's return portret here. Okay. So now if this is a little bit fuzzy to you, you can run these lines individually. Just pass in your own parameters, if that makes sense, just line by line. But we're going to just test it real quick here. So we're just going to call this object test. Okay. And RandomSim, we're going to pass in a seed of 1. We're going to tell it num assets equals, well, num assets. We already have an object called that. Where the probability of going long is 1, right? Okay, we're going to do a long-only portfolio. Maximum weight 50%. And then we're going to pass in our stock returns object. Okay, now if we run that, let's check it out. All right, so there is our portfolio return over time. Pretty cool. All right, and it's actually an XTS object, which is nice, so we can plot it, and you can see exactly that's exactly our portfolio return if we had those weights over that entire time horizon. Pretty straightforward. So let's move on, and we can plot this result. We can plot the cumulative returns as we are running the function. I'll show you that in a minute. But first, let's just do the bare bones. So let's run in the cloud. Result equals mapply, right? So retrieve the data and store it, and data equals 1 to numsims. Okay. And this is just going to essentially run our function with this parameter as the only variable. Okay, so if we're running, let's see, length. We're running 1,000. We're passing a vector from 1 to 1,000 essentially. So every simulation is going to take one of these numbers, 1, 2, 3, 4, and it's going to pass that in as the seed. Okay. Now you can pass in any seed you want. You can do R norm of that number and multiply it by 1,000,000 if you want. Unique random numbers, you can do that. But this is generally the safest way to go. Now remember, every time you run this, it's going to give you the same result if you use the same seed. So if you don't want the same seed, then increment it by 1,000,000 if you want it. But I'm not going to do that. So we're just going to do our function here is called RandomSim. So it's going to apply to our RandomSim with this data, 1 to numsims, and it's going to pass that in as the first argument, which is seed. Now that means we have to define all the other parameters. So we have to tell it what num assets is, what prob long is, what max weight is, and what stock returns is. Otherwise, it's not going to know what to do. So now we're also going to say dot parallel equals is parallel. So obviously we want to run this in the cloud if we are running a cloud solution. Prob long equals 1. Let's do num assets equal, that's right, we already have a parameter for that. And then let's just say max weight equals 0.5 again, okay? And now our stock returns is obviously our stock returns object. And then now what we're going to pass to the cloud is some additional parameters here. So parops equals list. And there's a few things we can do here. We can actually tell it, take a callback function and run a function every time it returns, which is how we're going to generate a dynamic plot. But first, remember that you have to tell it which packages you need. So options.packages equals list. And remember what we use for that function? Well, it's our portfolios, and it's the XTS package. Okay? And the XTS package could be included in QuantMod or Performance Analytics, but I think it might be a little bit more straightforward to just tell it to use the XTS object if that's the only thing you need. And then we're going to go ahead and run this. Now, there's other parameters we could also add, which we'll get to later. So, all right, so we're just going to go ahead and run this function here, and it's going to send the all the parameters to the cloud. It's going to execute our function, and it's going to return our results in our result object. So just bear with me here as this runs. I think I might go ahead and speed this up just for the sake of the tutorial. I hope you understand, even though it's just a few seconds or a few minutes, depending on how long it takes, it's just going to be easier for you guys to watch. All right, so you can see that took a few minutes, but it's certainly faster than running it myself. This would have taken about 18 minutes of CPU time to compute. And it instead took about 17 seconds of CPU time. That's about a 65 times speed up, which is fantastic. And now we have our results. So if you just check out the result object, you can actually see it's a matrix. And it's huge. So if we do dimensions of matrix, it's 1,000 by 4,300. So just to make this a little bit more manageable, let's combine this into an object, right? So let's do result.zoo equals as.zoo transpose our result. Okay? So now we have a zoo object, which you can see here if I do head. And actually, it's going to be a little bit easier if we do index of result.zoo and just set that equal to the index of our stock returns. So obviously, the dates are going to be the same as the stock returns. So, and actually, let me just return, let's say, the first 10 columns, just so you can first going on here. So you can see the column name is the parameter that's passed in, so that's the seed. So you can see for each seed we've got a different portfolio path, and that's going to go all the way through our data set, and let's do 1 to 10, all the way to the current day. Now something really interesting that we could do is plot the results as we go. So first of all, let me just let's do a quick chart here. So we'll do charts.performance summary, and we'll pass in, let's say, the first 10 paths, just so we can see what's going on. We'll just say cumulative performance, and we're gonna say geometric equals true in this example. And there you go. There's our 10 paths from our simulation that has been returned. Now, if we want to plot as we go, we're going to have to create a function that our mapply function can call every time it returns. It's a callback function is what it's called. So let's go ahead and do that. So we'll just call it plot prices. All right, plot prices, and we're going to make it of pre-results. So essentially, as we're getting results, from our Techila call, from our plyr call, just use what we've got. All right, and I'm going to tell it run invisible. So this means it's not really going to return anything to our space inside these brackets, but we're going to do lines. So draw on a current plot. All right. As.zoo, and then we'll just do cumprod of, that's the cumulative product of 1 plus our pre-result, so 1 plus our returns, of course. And now just something kind of funky we have to do is subset the pre-result, just because of the way that it's returned from the cloud. It's going to be a list, and then we'll subtract 1 at the end, of course. And then now let's just say, let's make it semi-transparent, right? So we could just make it black, but then you won't be able to see, the paths on top of each other necessarily. So let's do adjust color, and we're gonna just say let's make it black, but let's make the alpha. Let's make, in a sense, how see-through it is, 10%. All right. So alpha of 1 would be, completely solid. Alpha of 0 would be completely transparent. And then we'll just return the pre-result. Okay, so now let's go ahead and run these lines, plot prices, and of course it won't do anything, it's just a function, but let's actually just generate a base plot. So generate base plot. So we're essentially saying build a plot, but we're going to say make this plot empty. All right, but use our, remember that test object we made? Use our test object, and let's do cumprod of 1 plus test, and then subtract 1, right? It's going to be essentially the same thing as before. Maybe let's do our y limit from -1 to 10. I don't know how volatile the stocks are that you use, but you might want to increase that. How high should the limit of the chart go, and how low should it go? It depends on your time horizon as well. And then we'll just say, let's do ylab equals cumulative return, right? Just label the y-axis, and then color equals, and then we'll just steal that adjust black, right? And we're going to paste that there, but we're actually going to say make it completely transparent. So now we have essentially an empty plot, but it's got the right time index here. It's got the axis ready to go. And then when we run our lines function, right, our plot prices, so if we ran plot prices of our test object right now, actually we're going to have to make it a list of our test object because that's how it's going to be returned from the cloud. Then you can see, I don't know if you can really see it here. In fact, let me just run it a few times, which will actually just plot it on top of itself and increase the opacity here. So now you can see it's drawing that line. Every time it runs, it's going to draw that line. Now, if we did, lines of test, +1, it's going to be on a different area of the chart, right? Oh, whoops, that's going to be huge. Let's do +0.001. All right. There you go, and you can see that even that small return over time is generating a huge divergence, but that's okay. So we'll just run this line again. There you go. There's our blank plot, and now we know our function works, so we can pass that into our mapply call, and we're going to add it here in the list of parops. All right, and we're going to just say .options.callback. Oops, misspelled callback, equals, and then we're just going to pass in the name of our function, plot prices. So what this is going to do is each time our process runs, it's just going to chart a line, right? It's going to call back our function, it's going to chart a line, and that line is actually going to go on the base plot that we ran before, which is fantastic. So we're going to go ahead and run this again, and I'll be back with you in a few minutes, but I'll fast forward this so you can see it's actually plotting as we go, which is fantastic. If you run something that is, millions of simulations, if it's even after acceleration going to take a really long time to run, or a few minutes, maybe 30 minutes or something, then you want to see the results as they go, so you can stop the process if you've messed up. Maybe you forgot a parameter somewhere, and or maybe the function is just being crazy, right? When I added 1 to those returns, it was just going off the chart. And if I had seen that while we passed it to the cloud, I would have been able to stop it. If I wasn't running this dynamic chart, then I would have had no idea, and I would have had to wait until the entire process was done running, and then I saw the results to catch it, which would be a bummer. So we're just going to let it run here, and you'll watch it chart as we go. So here we go. There's already a bundle of results, which is fantastic. Everything looks like it's running okay. You can see some really similar paths here, and they're kind of aggregating over time. So I'm just going to go ahead and fast forward, and we'll see the finished results here, and then we'll move on. All right, so here you go, and you can see that even with our charting function, we've still got a 70 times acceleration. Now it's a little bit less, because we're aggregating the results and things like that, but still fantastic. Now let's move on. Let's go to our 2-parameter example, right? So let's first create a vector of constraints. So let's say, for example, I want max weights to be anywhere from, I don't know, what's 1 divided by num assets? That should be our minimum, right? Equal weight in every asset. Let's see what this is. All right, so yeah, we'll just run anywhere from 12.5% to, let's just say 15. We'll go up to 20. I mean, you could create a sequence if you wanted using the sec command, but I like doing this by hand just to see exactly what we're passing in. And let's do 0.25, 0.3, 0.35, 0.4, 0.45, 0.5. Maybe you could throw in some other weights if you want, get creative. Or maybe you want to change a different parameter. Maybe you don't want to change max weights. Maybe you want to change the number of assets. Maybe you want to change the probability long. Go ahead and do that. Create your own constraint that you want to change. And we'll pass that in here. Just remember that everything you do with max weights, instead you'll do with your new constraint that you're changing. So now let's create all possible combinations of parameters. So this is otherwise known as a parameter grid. So we're going to call this param grid, and we're just going to use the handy function expand.grid. That's from our base in R, and we'll just say seed is 1 to num sims, right? Just like before, same seed that we pass in, or you could pass in something different if you want. Now our max weights equals max weights. And we're going to go ahead and run this. And when you observe the object, let's see, head of param grid, you can see we've got all possible combinations of seed and max weights. Look, so it's going through 1 to our number of seeds with a 12.5% weight. But if you look at the end, or here, let's do tail param grid, you can see it all goes all the way up to 0.5. So if you do dim of param grid, you can see we've got 9,000 possible combinations, which is of course a huge number to run because our time series data itself is several thousand rows. So it's essentially 9,000 times several thousand rows. I think it's like 2,000 rows, 2,000 days. So we're going to go ahead and run the simulation in Techila. And so this is going to be a little bit more interesting than before, just running a bunch of simulations. This is going to be running a bunch of simulations while tweaking parameters to see what effect that has on our simulation. So we'll just do .data equals param grid, right? So remember before we just passed in the seed. Well, now we're passing in essentially a matrix of parameters into our function. So the first parameter is going to be seed. The second parameter is going to be max weights, which then goes into our function. So then our dot fun is, of course, the same function as before, RandomSim. We're going to do dot parallel. In fact, I can just go up here and steal this, right? Because I am a lazy programmer. So I'm going to go ahead and steal that. Dot parallel. There we go. You can see our number of assets is the same. Now, max weight, that no longer is static. That's a variable. So we're going to take that out. So we're going to take things the same. Our options, we're going to pass in our portfolio and XTS as well. Let's just save some time, right? Because we're going to visualize this with ggplot. So let's just save some time. We're already pretty confident that this is going to be okay. All right, so and before we run this, I just realized we actually need to change this parameter max weight, right, instead of max weights, because in our function, function, that's the name of the parameter. So we have to make sure that that's what we're passing in, because it needs to know which parameter we're talking about. It wouldn't know what to do if we said max weights equals max weights. So that's very important. And we'll collect the results, and I'll come back to you when we're done. All right, so you can see our results here. Speed up of about 75 times. Now, it took a little bit more than 2 minutes and 30 seconds, but it would have taken over 3 hours of CPU time to run this on my own machine. Now, let's just observe this object that was returned here. So if you do dim of result, right, that's our if you multiply each of these dimensions by each other, that is how many calculations was run. So you just do cumprod of that, right? So what is that? That's 38 million calculations, because we've got time series, and then we've got our two dimensions, one being seed and the other being max weight. So that's why this took so long to run, and of course that's why distributed computing is so useful. So now let's aggregate our data and visualize it. So let's just do pre-allocate. Let's just call this melted path, and we'll make it NA. So what I like to do is when I create an object, before I actually fill it, I'll just say it's NA. And now we're going to fill it with values by looping through each weight parameter, through each weight. And then we'll just do a for loop here. Now, for I in 1 to the length of max weights, right? So for every index in 1 to the number of max weights. This allows us now to extract our returns for each weight parameter. So you can see we've got a 1000 by 9 by 4312. Now 4312 is the number of days in our data set. I just happen to know that. 9 is the number of weight parameters we've got, and 1000 is the seed number. So if we index by the second dimension here, then we're going to be indexing by weight, which is exactly what we want to do. So now let's just do data.frame, and then we're going to apply, or no, actually let's do transpose our result in 2D, and then let's take the second dimension. So we do comma I comma, right? So we're just indexing one of these dimensions. So for example, if we just do result 1, right, comma 1 comma, then you can see the dimension here. Now we've got 1000 by 4300. So it might make more sense to transpose this, right? Because time series data normally has the date as the row, and then the index by column. So that makes more sense. So we'll transpose it, and then we'll turn it into a data frame, of course. And then from there, we're actually going to create a new object called path. And we're going to do a zoo object, and then we're going to apply to our pathrets object, which we'll then add 1 to, because we've got our simple returns now. Then we'll add 1. Then we'll say go across each go across each column and do cumprod, right? So this is of course just our cumulative returns, and then subtract 1. So this will get us a cumulative return for every single path in the selected index. Now we'll do index of path equals index of stock returns, right? Just so we can format it nice. And now we've actually got 4,300 data points for every single time series that we're using. So we don't really need all of that. Now, in order to calculate cumulative returns, of course, we need to use every point. But for once we've already got the cumulative returns, now we can just index it on a monthly basis. So let's go ahead and do that. which will just reduce our number of data points by a factor of 12. Why not? So we'll take our path, and then we'll just do OHLC equals false. And path is from, I believe, from QuantMod. Let's see, or 2.monthly is, I believe, from QuantMod. So let's see, 2.monthly. Oh, it's from XTS, which is bundled in with QuantMod, which is really useful. And now we'll just say path.monthly.df equals data.frame of path.monthly, right? Well, in fact, I mean, we could combine those two lines if you want, but I'll just do this for the sake of transparency. And then path.monthly.df, and then we'll do $date. So this is for ggplot. Our date object, or our dates in a zoo object are not going to be plottable. We have to pass it as a data frame. So then we just need to create a new column that contains our dates. Pretty straightforward. Now this is our monthly dates, which is why we index by month first. And then now let's do path.monthly.df $max weight, right? So we'll just label this max weights and then I, so which max weight, right? So obviously we're indexing through max weights, so we need to make sure we're passing in the right parameter there. And then we could even do an average if we wanted. Maybe it's going to make more sense to plot the average path across all simulations for selected weight parameter. And then we can index our object from 1 to the number of sims. And then let's do just the mean. All right. And then let's do melted path and just R-bind all of this together. So we'll just R-bind it to the melted path, which is, of course, remember, that was our pre-allocated object. So this means that every time we go through the loop, we're going to R-bind it to itself, just add another row, and then we're going to actually melt our path monthly data frame, and then id.vars. So which variables should be used as an ID? Now that's our date, that's our max weight, and what else? Our average, right, is really important. And then everything else can be collapsed. So our variable name equals seed, right? And our value dot name equals return. All right, so let's just see an example here. So if our I equals 1, then our path is as follows, right? We've got our cumulative returns, and then now we index it monthly. We turn it into a data frame. We add our date column. We add our max weight column. We add our average column. So let's just do head of path monthly. In fact, let's do head of path monthly, I don't know, 1 to 10. Oh, and I just realized that, you got to close vector there. Delete one of these. So here we go. So what this is doing is adding a date column, right? Adding our max weight parameter for each iteration, and adding an average column for each iteration as well. So it's going to take the average across each weight constraint, all of the simulations, right? It's going to take the average and create its own path. Then we're going to melt everything together and just collapse it so it can be plotted in ggplot, which is going to look like this if we do head, right? So now we've got our date, our max weight column, our average column, right, for that parameter. We've got our seed, and we've got our return as well. And then at the end, you see this NA. We're going to take out that NA. So we're going to just do melted path equals melted path minus 1. And that's just because we had pre-allocated it as an NA, right? So we're going to go ahead and run this all the way through all these loops. And then we're going to see that our date, our max weight column, our average column, right, for that parameter. We've got our seed, and we've got our return as well. And then at the end, you see this NA. We're going to take out that NA. So we're going to just do melted path equals melted path minus 1. And that's just because we had pre-allocated it as an NA, right? So we're going to go ahead and run this all the way through all these loops. And this might take a little bit to run because it's going through every single data point at this point. In fact, we'll show you when this is done, which it just finished. We'll do dim of melted path, and you can see, it's a huge object, so that's why it took so long to run. Thank God we had acceleration capabilities. So now let's chart the averages using ggplot. Okay? So ggplot's a fantastic package for this kind of stuff. So we'll just do p equals ggplot our melted path. Then we'll say AES. So what parameters do we have? We want x to be the date. We want y to show our average, right, of all paths. Maybe we can group our objects by max weight. And then that should be good to go. And then now let's just do a line. Let's do geom line. And then maybe we want to color it differently. So let's just say AES color equals max weight, right? So every max weight will have a different color. And then, in fact, maybe we should create a color scale. So we'll say scale color gradient, and then let's just say on the low side, let's make it red. Okay, and then let's just do scale x yearmon. So what this does is it says, our axis is not going to be, numbers. Our axis is going to be a year, month, date format. So then we're going to go ahead and run that line here. And this will take a few seconds to render, but just hold your horses here. There we go. And you can see the effect of our max weight constraints on our portfolio paths on average. Now remember, of course, there's 1,000 simulations behind each of these paths, right? But this is on average what's happening. So as you increase your max weight, you're getting, it looks like, more volatile returns. But of course, over time, that leads to greater returns. And then, during the slowdown, and what is this? It looks like 2001 or 2. And then, of course, during the crisis, our max weight portfolios of 0.5, they're on bottom because they were most exposed. And it makes total sense. But you can run this with any parameter. So now maybe you can run this with the number of assets in your portfolio. I would say you'd probably expect similar results. Maybe you can run this with long and short parameters. And just let me know what you get. I'm really interested actually to see what you get. Now let's, you can chart all the results if you wanted to. You could essentially, let's just copy this line, these lines here. So all results, if you're interested. Now remember, we do have a lot of results, so this is probably going to be a little bit slow, but maybe, maybe we are interested in seeing every single path. So we'll just say y is return instead of average, right? So return means that we're going to be able to see the returns of every single path, because average was just, just a few. I think just 9 different constraints, and then we'll group by seed instead, and then we'll just leave the color and the scale the same, and we'll run that. And now this, like I said, is going to take a little bit longer because we've got way more results to go through. Now, while that's running, let's go ahead and work on performance metrics. So, I was talking about standard deviation and standard deviation. Are, you can translate that into a Sharpe ratio, and of course, if you're interested in finance at all, you know all of that. But let's just let's go ahead and prove that, and we can create some awesome charts using ggplot. So let's just melt again for performance metrics purposes. So now we're looking at different columns, right? So let's just do perf metrics equals NA, and just remember we're pre-allocating again. and then we'll loop through I in 1 to length, just like before, of our max weight. So for each max weight constraint, we're going to do the following. And the first thing we're going to do is calculate the, first we have to aggregate our returns, then we have to calculate our total return, our annualized risk, and our Sharpe ratios as well. So in fact, let's just steal this, right? So we'll be able to extract the path again. Now we've got the cumulative returns. We're going to index them again, and then we're going to go into return, and then risk, and then Sharpe ratio. And of course, this will be a Sharpe ratio without a risk-free rate, but to make of that what you will. So here's the result from our simulations before. Now this is a little bit messy. I think we could work on this chart and improve it a little bit, but I'll leave that up to you. Interested in making, you know, a better chart that shows all of the possible results. You know, maybe instead of geom line, maybe we do geom point, right? And geom point, turn these into points instead of lines, and that could look much better. But then you're going to have a disconnect between each return points. All right, so let's go ahead and calculate returns here. So we'll just create an object called return equals as.numeric tail, and actually let me just prove this too. So we'll do I equals 1. We'll run this. So we're just imagining that we are in the first iteration of our loop. So now if we do tail of path, and we're actually going to have to add 1 to that just for the sake of the calculation. Now let's look at the last day. So this is going to give us the most recent day if we do tail, comma 1. And then the next thing we need to do is raise this to the power of 252, right? The number of trading days divided by the number of rows in path, right? Just to annualize it, okay? And now that's going to get us some crazy numbers. So let's, we subtract 1, right? So boom, there's our returns. You can see 3%, 2%. That looks very reasonable. And then we're just going to make sure that it is a vector, right? So we're just going to do as.numeric. And the reason we're doing this is because we're going to put it into a data frame. So there we go. And we'll just copy that. And there we go. There's our return object. And so now let's do risk equals, and let's do something similar. So we're going to make sure that it is a vector as.numeric. And then we're going to apply, right, to path threats. Let's do path threats. Because we need to do returns in this example, not cumulative returns. So let's see, path threats. Let's go across the columns, and then we're going to apply the function std_dev.annualized. So that's a handy-dandy function from, I believe, performance analytics. Let's double check that. .annualized. Oops. Yep, performance analytics. And this just creates a scaled risk measure for us, which is fantastic. And speaking of scale, let's pass in the scale parameter equals 252, because that's the number of trading days. And then we're going to go ahead and run that line here. So you can see if we look at risk here. Now we've got some vol numbers for each of our simulations, which is great. It looks pretty reasonable. You know, the S&P is anywhere from 11 to, I think, 15% vol. I think it's normally around 12. And that looks like it's in line with these portfolios, which is good. Some of them are lower, which is also good. So now let's create a Sharpe object, which is kind of a roughshod Sharpe ratio measure. We're just doing return divided by risk, and of course there's going to be a risk-free rate, but for the sake of this tutorial, we just are going to ignore that for now. And then so there's your Sharpe ratios. And then we're just going to combine this all into into one data frame, right? So let's call this metrics df, and we're just going to set that equal to a data.frame. Let's do return column, and we're going to pass in our return object. We're going to make a risk column, and we're going to pass in our risk object. We're going to make a sharp column, and we're going to pass in our sharp object. And then we'll make a column called max weight, and we're going to pass in our max weights object, and remember to index it, right? And so now, if we run this line, you can see we've got, let me do the head of that just so it's easier to see. We've got returns for each portfolio, we've got our risk, we've got our sharp, and we've got our max weight constraint. And then it'll go to the next weight constraint, and it'll get new portfolios and calculate return, risk, and sharp. So now we got to R-bind this all together, of course, so we can keep all of the results. So let's just call this perf metrics, because that's actually what we need to call it, because that was the object, right, that we made NA here. So now we're just going to set that object equal to itself when it's R-binded. So we'll just say perf metrics, and then we're going to pass in metrics df. And there we go. Oh, perf metrics. Let's see. Did I spell that wrong? I must have. Or maybe I didn't run this line here. Let me try that again. There we go. So I just forgot to run that line, my bad. So there we go. So that's how it'll look. And then, of course, at the end, remember, we got to take that NA out of there. So get rid of that, -1. And that should be good to go. So let's go ahead and run this loop. And this, again, was going through every single portfolio, so this is going to take a few seconds, but there we go. There we go. The head, that looks good. Let's check the tail. That looks good. Let's check the dimensions. 9,000 by 4, excellent. And then now let's just chart the performance metrics. So we've already got this melted just because of the way that we constructed our data frame. This time we didn't have to use the melt function, which is good. So we'll pass in our perf metrics. We'll just say AES parameters are going to be X. We want the X-axis to be risk. We want the Y-axis to be return. And then we want the color to be determined by our max weight constraint. All right. So we're going to go ahead and run this, and then P plus, let's make it a point chart or a scatter plot, I guess you could call it. And then alpha, let's just say that we want these to be 50% transparent. And then we're going to add a scale color. Let's do a scale color gradient, and we'll just make the low value red. And we're going to let that run. All right, there we go. There's our efficient frontier. We've got risk and return. And you can see as we increase our max weight constraint, of course, we're moving further up the efficient frontier, on average. We've got a few portfolios that are outliers here. You can see a few blue dots in there. But for the most part, they're clustering up here. And then, as you lower your max weight constraint, then you're going further down the other edge of the efficient frontier. So it's a pretty effective way to restrict your feasible portfolios to get a different result. And now let's just, in fact, let me just copy this. Let's say color equals sharp now. And we'll do low equals red, but now high equals green, right? Because a good, a high sharp ratio is good. So we'll run this. Actually, we've got to run that line and then this line. and we should get a Sharp ratio chart. There we go. And you can see, of course, the higher Sharp ratio is towards the edge of the efficient frontier. No surprise. And we've got risk return. That's pretty standard. Now let's just take these two lines again. Paste it again. Now let's do risk in relation to Sharp ratio, but we'll color by max weight this time. And then low is red again. And then we're going to go ahead and run that. And there you go. So this is kind of a new result. So you can see as your max weight constraint changes, that's going to, as our max weight gets higher, then your risk increases. It's pretty straightforward. As your max weight decreases, then your risk decreases. And then we can also see a relationship between Sharp ratio as well. You can kind of see it's moving across this this line here. So this is a great way to analyze, statistical relationships. To just build portfolios and change some parameters. Maybe you've got a trading strategy and you're changing some parameters of your trading strategy, and seeing how that affects how that affects the performance of your strategy as a whole. It's very useful to use a package like Techila to accelerate this entire process, because the real key here is running a huge number of simulations. If we ran this with just 10 or 100 simulations, it might only take a few minutes to run instead of a few hours on a single machine. But our chart's not going to have any resolution to it at all. So the number of simulations is really important. So in conclusion, I hope you find this tutorial really helpful and inspiring. There's really no reason to be afraid of big data these days, because when you've got access to the power of the cloud to help you, this is really not that big of a problem. Unfortunately, these simulations are not possible with a large number of assets or a large number of possible parameters on just a single computer. That's where parallelization and scalable computing really shine. Otherwise, you're just going to have to wait for IBM to create a personal quantum computer, let's say. So please like and subscribe to our YouTube channel if you found this information really useful to you, and we'll send some more content your way. Please visit TechilaTechnologies.com if you're interested in learning more about their cloud computing solution. This is Dakota Wixom from QuantBros.com, signing off.